I don't know. Should we wait a couple of minutes? Should I think let's wait if I don't know if somebody else is coming. Okay. If it's okay. I just want to say a few things at the beginning. Maybe I can write some stuff in the meantime.
You will turn on the lights on the board.
Yeah. I'll just write some references and then we can start a couple of minutes. So okay, I'm done with this, so I'm happy to start.
Yeah, hello everyone. Welcome to the string seminar. Today we're happy to have Suvrat. He'll talk about information paradox, in particular
state dependence and its discontents.
I thought it's based on
Okay. Thank you. This is actually not a traditional seminar. It's more in the line of a journal club. As you can see from the references, I'm mostly going to talk about stuff that is 10 years old. And the objective of this talk is that, I think there are some interesting problems that many of us thought about 10 years ago. And I think they're kind of deep problems. Maybe they tell us something interesting about quantum mechanics or about gravity. Personally, I stopped, in fact, thinking about them about 10 years ago because it wasn't clear to me how to make progress. But it's still interesting to review them once in a while. And that's what this talk is about. So it's really a review of like older stuff. And the main point is to introduce this phenomena called state dependence and also explain what some of the problems are. Right? So the title I gave was state dependence and its discontents. Yeah. And so the point is to explain where this came from and what some of the unresolved questions about it are, which I think are interesting and deep questions. I don't know, as I said, I don't know how to make progress on them, but at least the objective of the lecture today, and I think it'll probably, realistically speaking, go on to tomorrow also, is just to introduce you to some of these problems. Yeah. Okay, this story starts many years ago, and in fact, it starts with this so-called firewall paradox. But the papers that are relevant here, as I've written, are these papers by Almeri, Marolf, Polchinski, Stanford, Sully, and Stanford. Okay. So many of you have probably heard about the firewall paradox, and there's one version of the firewall paradox that is actually should be attributed to Samir Mathur, which is about evaporating black holes. Okay, this talk is not about that. It has nothing to do with evaporating black holes. Let me just clarify that. So this is not about evaporating black holes. So, there's a version of this paradox that's sometimes incorrectly attributed to AMPS, which is Almeri, Marolf, Polchinski, and Sully. Although it's, they had very little contribution to it. It's really was a paradox that was formulated by Samir Mathur. And the paradox is, if you take an evaporating black hole and you look at some Hawking radiation here, then you can argue that this Hawking radiation has to be entangled with something behind the horizon. But you can also argue that for an old black hole, it has to be entangled with some radiation far away. So B has to be entangled with, I'm not talking about this, but I'm just reminding you what the paradox is. So it's clear what this talk is not about. Yeah, entangled with C and A. And this is, violation of what's called the monogamy of entanglement. And so, this has led to, now this is an interesting paradox. But the resolution to this paradox that I think we've understood for many years now, in fact, soon after, for maybe 13 or 14 years, is that degrees in freedom in C should be identified with degrees of freedom in A. Okay? So D of in C are redundant with degrees of freedom in A. So it might seem that there are operators here that commute with operators here, as would happen in local quantum field theory, but this is not how things work in gravity. In fact, operators in this bounded region C need to be identified with operators at infinity, which are A. And if you do that, this is not a violation of monogamy of entanglement, because these degrees of freedom and these degrees of freedom are the same. Okay, so this is a paradox that's sometimes called the firewall paradox, but this talk is not about that. This talk,
So the identification between A and C are, for example, like to the wormhole as in case of the island.
No. I think that you don't need the island for this. The island is some specific example of this that you get in some settings. This is a much more general phenomena, and it's simply the fact that if you write down, it doesn't. I don't think you need wormholes for this. You can argue for it more generally based on gravitational constraints, and it's It's not clear that in all cases you have a geometric picture that there's a wormhole that links these two. In some cases you do, like in this ER equals CPR story. But in general, it's not clear that there's a wormhole, but you can always show that operators here can be written as complicated combinations of operators here. In a sense, it's almost a version of holography, because it's telling you operators in the bulk are written in terms of operators at infinity. So it's not something we should be, it might seem surprising, but it should not be surprising if you think about it more.
Like a mirror.
Actually, it is true. The mirror operators also had this property, but this is a more general property, which is if you take operators in a compact region, then those operators always have to be identified with operators at infinity. This you can show also in empty, just in empty space, this is true. You could set up a version of this paradox even in empty space, and you could have, set up this, confused yourself by saying there was violation of monogamy of entanglement, by showing that just in empty space you could construct, construct entanglement measures that show the degrees of, so this doesn't even have to be a black hole horizon. You don't even need that. So this is, and it's a very interesting property. I agree, and I've spent a lot of time also thinking about it. But this talk is not about this. Yeah? It's an interesting thing that we should talk about, but not today. Okay, so this is about these. So these papers, these by AMPSS, were about what are called large black holes in ADS. Okay. So large black holes in ADS have the property that there's some barrier here, right? I don't know where the barrier is. Here, maybe.
Yeah.
Okay. Okay, good. Okay, so it's about large black holes in ADS. Large black holes in ADS have the property they don't evaporate. So we don't have an information paradox for them in the traditional sense. But the question is, if you take a large black hole in ADS, do they have smooth interiors? Do they have empty interiors? And in fact, something that Polchinski used to say was, does ADS-CFT describe, or this is alternative framing of the problem, does ADS-CFT describe their interior? Okay. So maybe ADS-CFT is incomplete. Yeah, maybe it doesn't describe the interior of large black holes in ADS. And so this is the kind of question that we're addressing. I'll make it a little more precise. Empty actually means that it's the metric looks like the metric that you would expect by the Kruskal extension, and you don't have singularities. If you compute the stress tensor on a Cauchy slice, you don't find that it's singular. It's just just what you would get from empty space. I'll make it more precise in a minute. Yeah. I mean, empty meaning as long as you're close to the horizon, there's nothing around the horizon. Not what happens deep in the singularity. So this is just a statement that while you're near the horizon, that the experience you have is what we expect, which is the horizon looks like empty space. Yeah, effective field theory works. Okay, so the idea is that you take a state, so consider a typical state. Okay, so it's important that all these, all these paradoxes are about the so-called typical states in the CFT. Okay, what does a typical state means? It means the following: you take a state which has the property that its expectation value is much larger than n. Here I'm using n as what would usually be n squared in the in n equal to 4 super Young-Mills theory, but this is my large parameter. Okay, so this is a black hole which forms a this is a state which in the CFT we believe to be dual to a black hole in the bulk. Okay? So it's just a very heavy state. Much larger than doesn't mean that it has to be parametrically larger. It could be like 100 times n. Okay, and
Principle 1 over G.
1 over G Newton is in where you set ADS scale to be. No, I don't. I don't think you want 1 over G. What do you mean 1 over G Newton?
I mean the action in some sense.
It's just let me, if I put n squared here, it's just that in n equal to 4 Young-Mills theory. Let me write this as curly n. Let me write that as curly n. This would be a black hole which is of mass n squared or mass 10 over n squared, or what, 10 n squared. The n squared, it's really the central charge that's important. You just want the radius of the black hole to be larger in ADS.
That scales like 1 over. I mean, the gravitational term.
Yeah, you could say it's 1. Yeah, but I just want the black hole to have a radius that is much larger than ADS. But sure, yeah, you could say much larger in ADS. You could it 5 or 6. Yeah. 5 or 6 is fine. You just wanted you want, that's right. So you want it to be much larger. Yeah, I'm sorry. Why am I hesitating about maybe 1 over G Newton is
LADS over G Newton is correct.
Yeah, maybe LADS over G Newton is correct in units. Yeah. Here you don't need the string coupling to enter here. It's just 1 over G, just a gravitational effect. It just works in general relativity. So you don't care about the string scale. But okay, but there's also you don't care what, I mean. So if we had large lambda, and we don't, I mean, the string coupling only enters through G Newton, not through anything else, not through separately through a string scale.
So this n has a combination of the.
Just n is really just n squared. It's just it's just a black hole in a. No GS. This is just n squared. Literally just n squared. This is like the S. This is the SUN. So it's just a state which has energy which is much larger than n squared. It's what you just want it to be big enough so that you have a big black hole in area. So it's just.
You have to have some units, right? Because energy has units.
It's in units where I've set like the boundary. Sorry, so the boundary is on an S3 of radius 1. So it's a CFT, but the boundary is in. Okay. Are there any other questions, sir?
Actually,
Lambda is not here. You're in a you don't need lambda here. So you're in some regime where effective field theory works. So you're in some regime where lambda is large, but you don't need lambda here. It's just why do you need lambda here? Lambda is not here.
Newton involves GS.
It involves some combination, but we don't need lambda separately.
So basically, the n square is basically the ratio of L Planck to LADS.
It's the ratio of L Planck to LADS. That's right. Yeah. It's just It's L. So this is LADS by L Planck. It's some power it's some power which depends on the dimension, but it's that's all. Yeah. Okay.
So GS of order 1 is also
okay. Okay. I mean, usually we would not want to keep GS of order 1 because I don't want. But I don't necessarily want to keep GS. Yeah, but I mean, I don't want to keep GS of order 1 because then I might be worried whether Einstein's gravity is a good approximation to this. So I presumably want to keep GS small. Which is what? No, but Ashok also wants string scale to be L Planck. Ashok is saying G. No, he also wants L string to be L Planck. He's saying, what if GS is order 1? So we want to be in a situation. This is actually a bulk analysis. We want GS to be small. So we want effective field theory to work. So we'll keep GS to be small. We don't want to be in a situation where L string is L Planck. Yeah. It's some power that I don't remember. That's what Sharp said. Yeah. Okay. Maybe one of you remember. power. I don't know. Does one of you remember the power immediately? Probably d minus 2. Yeah, it depends on. Okay, let me keep it to be sharp. Yeah, so I don't write something wrong. Okay, good. So so we know what this is dual to. We know what the bulk dual is, at least for the cases where you're just looking at the exterior of the black hole. Okay, so we know that this in the bulk is. Oh, sorry, I was about to say typical state. Sorry, so we want to look at a state here, but I'm not being specific about which state I have. Okay? So the idea here is that you look at some state where all these EIs roughly have this energy. They can have some spread, but you're not very specific about which coefficients AI you're picking. Okay, so you can pick these with the Haar measure. So it's important that we are not very specific about which particular state. It's not one state. We want to look at the entire manifold of states, and we want to say that all these states, we want to ask what is the dual to all of these states. The reason it's possible to look at all these states together is that general properties of statistical mechanics tell you that for almost all observables, one choice of such coefficients leads to a state which is effectively indistinguishable from a state which you get by choosing another set of coefficients. Okay, yeah. The Haar measure is on is just on the Hilbert space. So this Haar measure is just d2ai into delta of ai squared minus 1. This is the Haar measure with some normalization that I again forget. Yeah, it's a finite dimensional space. The entropy here is always finite. All states, but this because I'm on my boundary theory is on some compact manifold. There's a finite energy gap. And the set of states is finite. The Hilbert space is finite. I'm looking at states in a band. It doesn't have to be order 1 actually. It could be order square root n, for instance. Much smaller than n itself. Okay. Okay, so this is my Haar measure, and I'm allowed to look at states. I'm allowed to look at any state that I pick from this band. Okay. Is it and the property of these states is that if you look at the reason I'm allowed to pick any state from these band is because if you look at any projector, first of all, and I take that Haar measure, let's call this d mu. And the first thing is that, if I look at any typical state and I average over all such states, then you would find that this is the same as basically taking the trace in the microcanonical ensemble of the same projector. So here I pick these states in some band with the Haar measure, and the first thing to say is if you look at the expectation value of any projector. So remember, in quantum mechanics, measurements are always made using projectors, and I look at the expectation value of any projector in one of these states, and I average over all such states. You will find that this expectation value is exactly the same as the trace in the microcanonical ensemble. But that's fine. You might say, well, maybe sometimes you get large values, sometimes you get small values, and you get an average of this kind. But in fact, there's a stronger result you can show, which is that this minus the expectation value of P, if you take this and you square it and you average it over d mu, then you get some number which is smaller than or equal to 1 by e to the s into actually e to the s plus 1 or something, but that doesn't matter. Yeah. What this averages over all these states using this Haar measure. Which P average? This P average is this because these two are the same. So this is P average. Okay. So what this tells you is that not only is it the case that the average on the average such states, what is? E to the s is e to the n squared. Yeah, s is n squared. S here is actually, I like to use n, so rather than n squared, so I'll use s is like some number into n. I'm sorry, I'm dropping all these factors, but they're not important here. Yeah? Okay, so what this tells you is that not only is it the case that on the average such states look like the microcanonical ensemble, but if you look at the deviation of such states from the average, the deviation of such states from the average is suppressed by 1 by e to the s by 2. Okay. So on the whole, if you look at this Hilbert space, you can think of as a copy of Cp e to the s minus 1. I like to think of it as a sphere. And if you think of it as a sphere, the sphere is basically a featureless sphere. Okay. And maybe once in a while, there are some very atypical states with respect to some observable. But those states are very far and few in between. Most states in the Hilbert space basically look the same. Okay. They're indistinguishable from each other with respect to almost all observables. Okay. Therefore, it makes sense to talk about typical states in ADS-CFT. That is because you have a situation where you have a large entropy, and it makes, because of these statistical mechanics results, it's reasonable to talk about the set of typical states without saying I'm speaking about one state or another state. Okay, is this point clear? This point about typical states is an important point.
Writing various paper, some
on counting entropies and so on.
Distinguishing sort of stringy or some of class of observables which are which enable you to distinguish.
You can, of course, distinguish a typical state using some of, for instance, if I give you a state psi and I give you another state psi prime, then it's true that if I look at the following projector, psi, then this projector, of course, clicks on psi, but might give you 0 on psi prime. So given a state, I can always say, well, there is some observable I'll pick that's specially attuned to the state that will tell me I'm in this state and not in that state. But if I pick my set of observables ahead of time, I say, here is the set of observables I'm looking at, then, almost all states are indistinguishable. It will still be the case that there'll be some states which will look very special with respect to those set of observables, but those are really far and few in between. That's what these results are. Just observables? No, it doesn't matter. You can pick any observable. So this is a result that holds true for any projector. But the only thing I'm not letting you do is I'm not letting you vary the projector with the state. So I gave you a projector. So any observable is a projector. That's the most general observable we have in quantum mechanics. So you give me any observable in the CFT, and such an observable will have the property that almost all states will look the same for this observable. So this is an example of an observable that can distinguish two. Doesn't matter. I mean, correlators are, in the end, in quantum mechanics, what you measure are projectors. I mean, correlators are expectation values. But you see, that doesn't require you to be local. I took any projector. In the end, what you measure in a correlator is, what you mean is I have a product of operators, and then I make a measurement and I get different possibilities, and the probability of getting any particular value is given by the projector onto the corresponding subspace, and therefore a projector is really the most general observation you can make in quantum mechanics.
Doesn't the second statement hold under some conditions?
This requires no conditions. It's very general. This is just true. I mean, the only thing I assumed for this was that the eigenvalues of P were, not larger than 1. That's the only thing that you need. This is, I mean, it's really a very powerful result. It's the fact that in a Hilbert space, in a big Hilbert space, it just is the case. I mean, it's a very simple result also, that most states are not distinguishable from one another. If you pick your states, your observables ahead of time. Of course, if I say, can I cycle through my space of observables to identify a state? Yes, you can, as this example shows. But this observable, for instance, just gives you 0 on most states. So it's not in contradiction with this result. Yeah.
So this psi has a summation. I mean, there are infinitely many.
Not infinitely many, finitely many. E to the s many. Yeah.
There are not fields that are orthogonal.
Yes. Which are orthogonal. Yeah, they are orthogonal. There's no problem. That psi and psi prime are also orthogonal.
They are then not the same state.
I never said they're the same state. I said that so this is a projector, okay? So actually, this is maybe useful to say. You see, what are the rules of quantum mechanics? What they tell you is, you give me any operator O, right? I take O and I have to write it as, some sum of AI times PI. Right? This is just, so maybe actually this is worth saying because this talk is going to be about the Born rule. So let me just say this. So usually we say we measure operators O, but that doesn't mean anything, right? We talk of especially in particle physics, we're used to talking of expectation values of O. Okay? Actually, that's not what quantum mechanics, that's not where it starts. What you say is you take a Hermitian operator O, you write it a sum of AI, Pi, where these are projectors. And then what quantum mechanics tells you is, if you measure O, you get the value AI with a probability that's given by the expectation value of Pi. So the data of measurements is really, that lives only in the probability distribution, not in the expectation value of O. Okay? You see, it's not like by saying that I change my scale of O, let's say I multiply O by 10O, two states that were less distinguishable earlier become more distinguishable now, right? Because what I have is, what I really measure are not expectation values, but what I really measure is the probability distribution. So it's not that, by measuring, by multiplying this operator O by 10, I make things. So what this is telling you is that the probability distribution for any measurement is always, if I pick my measurement ahead of time, then the probability distribution is almost the same on almost all states. Yes, you can, but I want to emphasize that these eigenvalues are kind of in your hand, and they are a little misleading when you speak of how distinguishable or not distinguishable states are. What is really important, the physical part comes with the probability distributions, and the probability distributions have the advantage that the probability is always between 0 and 1. So, if I put in an operator over here, I'd get some standard deviation here, which might be confusing. So what I'm saying is that in terms of probability distributions, almost all states are the same as one another. Yeah, so you measure probability distribution. You're measuring, you mean you're not measuring the probability distribution, but you'll measure the relative frequency.
Which is measuring this.
Fine. You'll measure the relative frequency. I want to here focus attention just on the projectors rather than the eigenvalues. Just because, I want to avoid confusion coming from the fact that some of the eigenvalues might be large. This will also be important later. Okay? You're right that you measure the expectation value of P. That's what you're saying. Yes. Yeah.
But somehow you're talking about CFD, not just quantum mechanics.
No, it's just quantum mechanics.
I mean,
It's just quantum mechanics. Huh? It's just quantum mechanics. Why not? It's still quantum mechanics. It's not quantum mechanics. Huh? It's on a sphere. It's quantum mechanics. Why is it not quantum mechanics? It's discrete also. Everything is discrete. It's nice quantum mechanics. No.
Yeah, but it will still fit within all these analogs. So you have special properties of this one that are not from locality. But you're saying you cannot distinguish this.
No. You cannot?
The question is, they can use the extra structure.
No, because this is true for any projector, right? Any projector, there might be extra structure, but any projector has the property that if I look at a typical state, one typical state is indistinguishable from another typical state. I want to be careful once again. Just keep this example in mind. So maybe my words these equations are true, and maybe my words might be confusing. The statement is that if I take, let's say I fix ahead of time some measurement I want to make. And I pick one typical state and I pick another typical state. The probability that I'll get a different answer, and when I say probability as measured by the Haar measure for those two measurements, is extremely small. Most likely, I'll get the same answer with an accuracy of e to the minus s by 2. There is some probability that I'll get a very different answer, as this example shows. Let's say this was my measurement I was making, and the state happened to be this. Then I would get an answer which would be 1. If the state happened to be psi prime, which was orthogonal to this, I'd get an answer that's 0. So it is possible that for an observable, I might find a state which maybe I get suddenly 1 in some cases and 0 in the other. But most states look the same.
So if you had a projector whose rank was comparable to e to the s,
Doesn't matter. How does it matter?
If it's like
This-
after things,
Then it'll just click. Yeah, so it'll click on half. It'll not click on half. So for most states, it'll just give you half.
It's a linear combination from both.
Most states are linear combinations of both, exactly. If you look at the set of states which are only of one kind, that's codimension 0. So most states are basically linear combinations, so you'll just get half. It's kind of a boring result, but yeah.
If you have of the same order as e to the s, but missing a few.
Yeah, then you'll get that fraction. Yeah, exactly. So on most states, you'll just get that fraction that you're talking about. You will find the projector just gives you the fraction alpha that you had. Yeah.
Yes, taking like a basis, right? So you have the energy basis.
I had the energy basis here. Yes.
Then
Over
every
the
part-
yes. So I take the energy basis. I didn't write it completely precisely. I said pick these, but then there should have been a range here, which is maybe E naught minus delta to E naught plus delta. This is my E naught. And delta is some number which is much smaller than E naught, but can be large. Yeah.
Okay, so from this year's, of course, if you're going to draw some sample from this, there are going to be a lot of similarities.
Correct.
So now, can you tell how is this S dependent on this delta?
How is this S dependent on the delta? Actually, S just scales linearly with delta. This is just a standard microcanonical thing. So S is the density of states. E to the S gives you the density of states. If you scale delta by 2, you'll just get E to the S into twice. I mean, this delta it's a question of how you define S exactly. But I could define here, in what I have done here, I have just defined E to the S to be the set of all states in this band. If you chose, a delta that was twice as large, then you would find that your S differs by a factor of log 2 from my S. But because S is n squared, we don't care about the log 2.
So basically, all of this is just a property of R measuring among the.
It's actually just a property of general high-dimensional Hilbert spaces. I'm sorry for spending so much time on this, but it's kind of important for what I'm about to say. Is there another question? Yeah. I don't know. It's this measure. Yeah, it's a okay. It's a uniform measure. Fine. Okay. Yeah. Yeah. Okay. Yeah. Fine. Yeah. Okay. It's just this measure. Yeah. Yeah. It's not the measure on the unitary group though. It's just the measure on CPN minus 1. It's just the measure on CPN minus or CPE to the S minus 1. Yeah.
CFT is just quantum mechanics. So what is the application? I mean, I understand you construct
it's the CF here. All I used was the CFT had a set of there was a Hamiltonian. Okay, it had a set of eigenstates. It has a set of discrete eigenstates. I summed over them. And the rules of quantum mechanics are the other thing I used was that if you make a measurement in the CFT, what the rules of quantum mechanics tell you is you measure an operator, you break it up in this way into a set of Hermitian projectors, and then you measure the expectation value of getting a certain answer. Or you measure the expectation values of those projectors, and that tells you the probability of getting the answer AI when you make a measurement. That's all I used. That's all I used about quantum mechanics. That's true for the CFT. The CFT, yeah, sorry.
Discretizing the spacetime into a lattice, and then reaching the CFT as a critical point of that system. Then you just have discrete degrees of freedom. Then it's just the quantum mechanics of many particles. Like one particle on each lattice. Sure. Yeah. So that's the sense basically.
In this case, actually, I don't have to discretize it. I just put it on a sphere, and the energy spectrum became discrete. I don't need a lattice regularization to say this. But you could think of it that way, if that helps. But to do this, I don't need a lattice regularization. I just need to put it in a sphere, and the energy eigenstate split.
We need for UV, but we are restricting energy band anyway, so you don't go to.
You mean to regulate something? It's a CF. Okay, yeah. I mean, if I wanted to calculate something, but I don't need the lattice to define the theory. The theory is just defined on the sphere. Yeah, you can think of it as a limit, sure.
This language, but not quantum field.
Yeah. I have this problem. Yeah.
Sorry, can I ask a question? How important is the Haar measure for typicality of states?
Sorry, there's some discussion here. 1 second. Just 1 second, please. It does. Quantum field theory is a subset of quantum mechanics. So all the postulates of quantum mechanics work in quantum field theory. Quantum field theory is not something that goes, you see, there's additional structure of locality, but quantum field theory is a subset of quantum mechanics which has some additional structure. Here I'm not needing to invoke that structure. Because you see, in quantum mechanics, if you can't distinguish states, it can't be that the additional structure will help you, right? I'm saying this is true for any projector. I didn't say that this was a projector of some kind. This is just, this is a very simple result. I could even prove it if you like. You basically just have to do those averages with a Haar measure. It's proved in that review I gave you. But it doesn't, the fact that you have additional structure can't help you if this is true for all projectors. So quantum field theory is just a subset of quantum mechanics. And if I'm saying I can't, this result is true for any projector. I don't need to say anything more about the system. On a Cauchy, I never said I don't need Cauchy slice here. They're just eigenstates.
You can say that, right? to help
I can say that. Yes, I can say that. So I'm in a boundary. But I have a quantum system, and on the quantum system, these are eigenstates of this operator H, which are energy eigenstates. You're right. You could take the boundary theory, and you could think of the Cauchy slice is just an SD minus one. So generally, you see, the way we think about this is that this is a theory that lives on the boundary of ADS. So this boundary is a sphere and cross time. So this is time. So the theory lives on this SD minus one.
Yes.
Yeah.
So you could probably reformulate this just as a statement in the vector.
Yes.
Without worrying about whether it came from quantum mechanics.
Yes. This is the statement just in the vector space. This is a statement. This is just a result of. It's just a integral. Yeah. Quantum mechanics. Okay. Yeah. There was a question online. Yeah.
Yeah, so I was asking how crucial is the Haar measure in defining typical states, or
How crucial the Haar measure in defining typical states? The Haar measure is quite. That's our definition of typical states. The Haar measure is important. It's kind. The Haar measure is whatever. It's just a natural measure. It's just saying that I don't pick the 101st energy eigenstate more specially than the 99th energy eigenstate. If you used a different measure and I said my 101st energy eigenstate was very special, then maybe that state has some special properties, right? But we don't want to say that. We just want to be democratic. So I'm a great believer in democracy. Okay. Okay. Right. Okay. 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 Yeah. Yeah. So the base is not important.
The basis, and if you project
Yes.
half of them,
Yes. Thank you.
then a typical
Yeah.
state could be another half.
Thank you. Yeah. This is invariant under unitary transformation. So this measure has the property that if you make a unitary transformation, it'll still remain the same measure in a different basis. Yeah. You don't need the energy basis. I picked it to define the measure. Okay. Sorry. So I have gone. Yeah. Yes. 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 Yes.
There's a kind of a thermal state.
Yes. The thermal state is close to the microcanonical state. So let me write one more identity. This is also equal to 1 by z beta, trace of e to the minus beta h, p. But these errors are actually small. These errors are 1 over square root s. So this Haar measure is the same as the microcanonical measure, the way I defined it. That is the same as the thermal state, but the errors between the Haar measure, the microcanonical state and the typical state are 1 by e to the s by 2. The errors between the typical state as I defined it and the state are 1 over square root s. I could define a different measure which would be close to the thermal state. The way I've defined it is it's close to the microcanonical state. But I will use the equivalence of ensembles at some point. So the microcanonical ensemble is also like the thermal state. And this beta here is just, the how s changes with e.
Yeah,
So it's just one.
I was
Yeah.
just wondering, like,
Yeah.
so
Yeah.
I think that should one, maybe typicality is maybe something set by deviation from thermal state. Could that be an alternative way?
No, I think these states also look like the thermal state up to 1 over square root s.
Up to 1 over
Up to 1 over square root s. So they all look like the. I mean, they all basically. Yeah.
You're kind of picking out some things, and then there's a notion of nearness.
There's a notion of nearness.
Nearness to them. And
Yes.
Then maybe you don't average it in quite the same way. I mean, like Ashok was saying, if you had a preferred kind of a slice in there, and then you said things which are very far from thermal, you kind of say they are not typical, but things which are closer to thermal, you say they are typical.
That's actually it's consistent with this. Yeah, because if there were states which so when you say very far and very close, you have to decide with respect to what observables. So let's say you fix some observable. Say I'm measuring the density, for instance. That would be an example of an observable here. Like what is the average density over this room? Then I could measure that, and I could say, well, here's a state which has the property that the average density is very far from the expected value that I get in the ensemble. That would be a very atypical state. And that's consistent with this. Such states do exist. Of course, you could find a state where the density is here, but it's a very small fraction of all states. So that's consistent with this. States which are very far, are very atypical, but they do exist. Okay, so let me go on. Let me at least frame the question. So this is, so, what do we, since I'm sorry for spending so much time, but some of these issues are maybe useful to discuss now. Hopefully we won't have to discuss them again when, so we know something about such states from the bulk, okay? We know something that from a lot of things we've learned about ADS-CFT, we know that if I take a state, a typical state of this kind, then such a typical state is dual to a metric which is basically a Schwarzschild black hole. Okay. So we know that such a state where this energy is much larger than n is dual to a Schwarzschild black hole in the bulk, at least as long as I'm outside the horizon. Okay. So this is something we know about the bulk dual. So this is a property of the bulk dual. How do we know this? We know this from many tests we've done with ADS-CFT over the years, and we know that thermal states on the boundary are like black holes in the bulk. Okay? And because any state on the boundary is like a thermal state with respect to almost all observations, it's reasonable that any state of these typical states is like a black hole in the bulk. Okay. Okay, so the question that all this asks is about the following. Okay, so we believe that if you look at the bulk, then there's some black hole here, there's some horizon, and how should I? So maybe this black hole was formed in the past. I could reach this typical state by exciting things at some point, and then I have this black hole, and I know that if you look at the geometry here at late times, then this geometry here is of this kind. Okay, so this is the Schwarzschild geometry. So the question is, is this diagram that we draw, this conventional diagram that we draw, is it correct not just outside the horizon, but also inside the horizon? Okay, so that's what the question is.
Why did you draw the shadings on that?
Sorry, the shading was some matter that formed the black hole, but actually I don't need the shading. I'm not going to make any, and I was trying to look at a late time that comes, but let me, to avoid confusion, let's just forget about the matter. The shading was, I was trying to think of a black hole which formed from collapse and then look at late times, but let's forget about the matter that formed it. Yeah. So the question is, does a typical state look like the black hole inside the horizon as well? Okay. So we know from many experiments, or not many experiments, many tests we've done of ADS-CFT, we expect that it looks the way we expect it to look outside the horizon. But does it look this way inside the horizon as well? Yes.
Can you tell why this test failed to tell you what happened?
Well, in general, if you have something inside, you can't usually, it's causally disconnected from what's happening here. So you can't immediately, you can't send a probe, for instance, inside and measure and let it come out and measure what's happening. So it's a more subtle question. I mean, for instance, if you wanted to measure what was happening here, you could have sent some waves and then detected their scattering here. And that would tell you that the geometry here didn't have anything special or it conformed to this.
So you're saying there is like very little, no idea of what exactly is doing?
Well, sorry, I'm not saying, I'll say what we know or what we think we know. Right now, this is the question. And all I'm saying is that this is a question that these issues are about. Okay, so this is the question, and let me make it more precise. So what does it mean to say that the geometry looks like the black hole geometry? One thing you could say is, can you define some metric, and can you use the metric and measure the expectation value? I'm going to use a slightly different probe, which is similar to this idea of just looking at the expectation value of the metric, but maybe a slightly more fine-grained probe, because it also looks at fluctuations. So I'm just going to reformulate that question. At least if at the end of this, the question is clear, that will be helpful. So the question is, yeah.
What I don't understand is like you have in the CFT,
Yes.
The quantum mechanics picture does not move.
Yes.
It's coordinate.
Yes.
So if I'm asking whether I can distinguish two states, states are the same as local operator, right? By state operator.
Okay.
So doesn't the OP know more about
I don't think so. I mean, if I proved a result which was a result for general projectors, then there is nothing more to say, right? Because the most general observation you have is a projector. So it's not like, it's not like I said that you have some set of measurements and you get some more observables. I made very little reference to the structure of this is basically a result about vector spaces, Ashok was saying. So in vector spaces, if you show that, if you show a result which is true about vector spaces or for all operators, there's nothing you're going to do in a subsystem of that, in a special kind of vector space where this result won't be true, right? You've collapsed space, but the space of observables I had, like this projector, could be one of your products of local operators, or it could be any of those things, right? It's eating all of those fall within the set of matrices that act. Doesn't matter, right? Even then, how does it matter? Because it's a result. It's every measurement that you make in quantum mechanics is always a projector. That's just a rule of quantum. No, but every measurement you make in quantum field theory is also a projector. It's not like in quantum field theory when we go to the LHC that we measure something that's not a projector. The basic axioms of quantum mechanics still apply. You're right that there are operators and we have additional structure. But if I prove a result about, for instance, let's say I prove that the Hamiltonian is Hermitian. That's true also in quantum field theory. So if I prove a result which is just a general result about quantum mechanics, and it also. No, but the result is true for all operators. No, it's not like in quantum field theory you have a more general class of observables than projectors. Projectors are the most general set of operators. So if I told you that something is true for all projectors, there's nothing more you can say. Because the result I proved didn't say which projector you're looking at. Any projector has this property. So any observable has this property.
I think maybe something like the S matrix or something like that.
Yeah.
Probably what he's trying to fit into.
The S matrix is, the S matrix usually you try to write as an expectation value of some things, some limit of expectation values using some, but when you measure the S matrix, what you really measure is what is the probability that two particles came out in one way and some other, and so it's really still measuring probabilities of projectors, right? It's not like you measure something else.
Yeah, maybe the point is imagine that you find out energy map, right? And you find that according to
Yeah.
How you can say you look at the energy items or not energy, look at states you can localize in a certain state.
Yes.
That will not be a typical state from the
It'll
original energy map.
not be typical. Yes.
So would that enter in this?
So you could ask that. You could ask for this kind of. But that's not a typical state in the way I defined it. So you could say you could look at special classes of states, and then you would have to define some Haar measure and prove something about those classes of states. But here I was looking at the set of all states. Here I'm interested in the set of typical states defined with respect to for instance, this is really a Schwarzschild black hole. You could have said, what about more general rotating black holes in ADS? Okay. So those are not typical states in the set of this energy band. I'd have to define a slightly different ensemble for those. So maybe quantum field theory allows you to define more general ensembles that have that, but I'm not interested in those ensembles. Maybe you could define ensembles of this kind where states are localized in some region or some other region or something else. But right now I'm not asking questions about it. Yeah, but I care about typical states. This whole thing is about typical states. So we are today talking about typical states. You might be able to talk about atypical states which have some property of being localized in some region or something, but that's a separate discussion. Here the discussion is about typical states. Okay, good. So I just want to reformulate that question, and at least I'm glad I'm managing to do this. So do there exist operators phi of xi in the CFT? This is a slightly confusing point, so please don't get confused. This xi is a bulk coordinate. Okay? So, but these operators exist in the CFT. You can always take a set of CFT operators and you can label them with respect to bulk coordinates. Okay? So the fact that this is an xi, this xi is not a CFT coordinate. All I'm saying is I give you a bulk coordinate, it's a label, it's a parameter, and I want an operator that corresponds to this label in the CFT with the property that in one of these typical states, if I measure correlation functions of these operators, they give you the answer you get by doing effective field theory in curved spacetime in the black hole geometry. Okay.
Don't want to formulate this in terms of projectors.
No, I won't formulate this in terms of projectors. I could formulate it, but I won't formulate in terms of projectors. Sorry. In the end, I'm also a particle theorist, so I like thinking in terms of expectation values. So I won't formulate this in terms of projectors. You could formulate this in terms of projectors. It will make some of the additional arguments that I'm about to make a little harder. You could formulate this, of course, in terms of projectors. Yeah. I could say that, let me not try. Yeah, okay, yeah. Okay, yeah. Huh? Excess can be outside or inside, yeah, where these can be outside or inside. Okay, okay, this is a version of, it's just a way of writing that question in equations, okay? So there's an unambiguous way in which you can do effective field theory in curved spacetime, and you can compute, yeah.
Isn't this what you actually mean by saying that the state is going to it's a black hole?
It's okay. I mean, maybe that's what you mean. Yeah, sure. So I'm just writing it down. You mean that's what? Yeah, sure. If you're saying this is obvious, that's fine. That's what you're saying. You're saying this is obvious.
Come out.
Yeah. These x's can be inside or outside. Yeah. You can compute, of course, effective field theory correlators outside or inside. You could take this black hole and you can compute a correlation function of operators outside or inside. In fact, the easiest way to compute such a correlation would be to extend this to an eternal black hole, which we believe also has the same geometry. And we are only, by the way, we only want this to work up to, I don't care if it fails at order 1 over n. Okay, let's just ask whether this works to leading order. Okay, so the scope of this talk is, can you find operators that have the property that this expectation value gives you the same as what you can compute unambiguously, what Birrell and Davies would tell you to compute, at least up to order 1 over n corrections. Okay, that is the question that I'm going to ask. And the answer I'm going to give you is that yes, if you allow state dependence, and no if you don't. Okay? Yeah. Yes, and the first part I'm going to say is no if you don't. I'm going to explain why the answer is no if you don't. Yeah. The left hand side is in the CFT. The right hand side is computed using Birrell and Davies. So I open my Birrell and Davies, tells you how to compute correlators in curved spacetime. I compute various correlation functions, one here, various things. Then I've computed this list. Yeah, I have it. Well, you have to produce the dictionary for me. I'm only computing the G's. Now you have to come and find some phi's with the property that when you compute these phi's in the CFT, you compute the expectation value, you will get the same answer as what I expected to get. If so, then I'll say, the dual of this state is that full geometry including the interior. I'll also say then the CFT describes the interior because you found for me operators that describe the interior. So this is the task. Okay, so this is the task. I hope this is clear. And you have to do this in a typical state.
Here this confusion comes.
Yes.
Think in terms of projector.
Yes.
Left hand side I can imagine you do it because you're defining everything.
Yes.
Right hand side probably is not well defined as a projector if some of the x's are inside or outside.
Why? It's still.
It's never observed. You cannot wait.
No, but it's still an observable in the field theory. If I just quantize the field, even on the right hand side, I think even the.
It's inside or outside.
I mean, I don't have to make a physical measurement in the formalism of quantum field theory in effective spacetime. It's a completely good observable. There's nothing behind the horizon is also good observable. No. In my field theory, I have my observables are local fields also. That's also a local field observable. I don't have to define everything in terms of infinity. You mean there's some issue of field redefinition ambiguities and so on. Otherwise, in my loop. Then now I'll take Pranav's point of view and I'll say that you can define local field operator. Yes. The projectors were not the projectors onto some subspace of the Hilbert space. But if I take a product of those operators, that product of those operators is also an operator. I can break it up into projectors. So I can ask about what the probability of getting a different value is. Maybe one thing to. No, why is it that nobody can measure it? If an infalling observer falls in, they can measure it, no?
On the right hand side, the input sample is
Actually, here I'm doing field theory in curve space-time. There's only one point, so I don't need to impose the, Hamiltonian constraint is just saying the equations of motion are satisfied, which they are satisfied for this geometry. Sorry, there are many questions. Yeah. Sorry, can I answer Ashok's question first? Yeah. If I'm doing field theory in curve space-time, then my field operators themselves are observables. The reason if you wanted to say this in terms of projectors, what you would say is that you could measure the expectation value of the operator. You could also measure the expectation value of the square of the operator and fluctuations. And what you should get right is not just the expectation value of the operator, but also all moments. That's the same as getting all projectors correct.
Yeah, but somehow what I'm saying, observables are observed by someone.
Yes, but here I wanted why somebody is an infalling observer for me. That's actually an important question. I want to ask what happened behind the horizon. If you don't allow me to ask the question, then there's nothing to say. So I want to ask, if I fall into the black hole, then I measure some operators there, what will I see? Otherwise, there is no question to ask. If you say I can't make a local probe, then there is nothing to say. But I want to say that I can measure an operator here. I mean, I can. If we say the metric is of this kind, if I say the metric is something behind the horizon, I should be allowed to measure the expectation value of the metric behind the horizon. It can't all be from infinity.
And that observer should also be able to see things outside before.
Yeah. So, for instance, if you take an observer here who falls in, before they end their life, they will have a record of all this. They will know the answer to the question, then they'll die. They won't tell us, but they'll know the answer.
Yeah, but not everything will be accessible.
Not everything will be accessible. So in fact, tomorrow I'm going to say a little bit about causal patches, about this issue of what happens if not everything is accessible. So this is a good point. For instance, if you want to ask what is physically accessible, there's a notion of a causal patch. Sometimes in the eternal black hole especially, we speak of operators which are outside a causal patch, which means that no physical observer can measure them. So tomorrow I'll say a little bit about that. Traditionally, it has been expected that maybe this should not be an important constraint. Although tomorrow I'll say a little bit about how it might be important, this issue of, what can one observer measure, or what can a group of observers measure, and at least they can get together and decide before they fall into a singularity. Yes.
Yes.
They are dressed. And that will be important in a minute. They're all dressed to the right boundary. They're all dressed to infinity. Yes. They are not local operators in the strict sense. They're all dressed to the boundary, and as I'll say this in a few minutes. Yeah. Okay, I'm through 1 hour. It is a local operator, except in gravity there are no local operators. It's the best example we have. What Loga is saying is they have to be dressed. You have to tell me how you pick the coordinate. So I'll dress everything to the right boundary. For instance, when I say x, what do you mean by x? So the way I'll define x is I'll say I shoot a light ray and I see where the light ray goes. So that's what it means to dress an operator. You have to specify what it is. You can specify it from infinity. You can say an infalling observer is carrying a clock. What do they measure after 10 seconds of falling in? By which time they might be behind the horizon. But this operator I just described is not local because the infalling observer started at infinity. But it's the closest approximation we have to local operators in gravity. Okay, let me at least get to a little bit of this thing. So okay, so this was the point. Now I'm going to make this a little more precise. The first point I want to explain is why the answer is no if you don't. Okay, why is it that you can't find such operators if
Can you say
we will come to that. Yeah. So right now, first let me answer the second part, and then we'll discuss this. Okay. Yes. Yes.
Remember keeping both the left side and the right side in this paradigm of quantitative the projector field
Okay. On the right hand side, I just have some numbers. This is just a number I computed using. It's extracted by doing quantum field theory in curve spacetime. Yeah. Yes, it's true, although this is an expectation value, but it's true I could reduce it to projectors. I could write it in terms of projectors, but right now I wrote an expectation value. What is the issue? I'm not. Huh?
You can write projectors using correlation functions, not the other way.
You could always write correlation functions using projectors. It's just an expectation value. I break it up, and this is just,
Why does that make sense? Because in the first place, maybe it's a very nice question. If you want to have this Cauchy slice and time evolution Hamiltonian picture. Why does that make sense where the space-time is not very flat? Let's say like close to flat, whereas like metric is, how do you even define this Cauchy slice?
First of all, the Cauchy slice we were talking about earlier was a Cauchy slice on the boundary when you said Cauchy slice. Here I'm talking about the bulk. So in the bulk, it's like how we do quantum field theory in our world in curved space-time, where we still have, we think we make sense of, So first of all, the expectation value here is an expectation value taken in the CFT. Yeah? On the right-hand side, I have some standard formalism of doing quantum field theory in curved space-time, which lets me compute expectation values of such operators. So I compute that. You're happy with the right-hand side?
There is a Cauchy slice, the bulk also. But is that so when you're inside the black hole and so there is a slice that just goes horizontally across from the left boundary to the right boundary. So there are spatial Cauchy slices that traverse the outside and the inside. There is a local, you see, there's always a local decomposition of the Cauchy slice times. Yeah. No matter how close you are to.
I'm not very close to anything.
It's a singularity then.
Yeah. So maybe this is important. I'm not very close to a singularity, right? So everything I'm saying here is going to be actually close to the horizon. Maybe this is one more point. Yeah. We are not close to the singularity. So this whole story has nothing to say about the singularity. It's a question of what happens when you are near the horizon, outside and inside. Yeah. Okay. Now I'm going to just refine this question. I'm going to massage this question a little bit. What do I mean by this? And so let me try and get my formulas correct. So we can define the following operators. Yeah. Let me take this. Let's say you came to me and you defined this operator phi. You said here is an operator phi, okay, which has this property. Then I can do some things with this operator. I can take this operator. I'm going to shift freely to now Kruskal coordinates. So u, v are Kruskal coordinates. Kruskal coordinates have the property that they vanish at this horizon. This horizon is u equal to 0. Here u is smaller than 0, here u is larger than 0. Okay. So I can take this field and look at minus u plus I omega minus omega. And this T of u is a smearing function. Okay, so this u goes from u equal to 0 to some value cut off, some epsilon. And this is like this picks up a certain mode of the field that oscillates with a frequency u to the I omega. Okay. This T of u is just a smearing function just to make sure that things die off smoothly at epsilon, and to make sure that this mode is normalized rather than delta function normalized. Okay, so let me write omega here. And similarly, I can define something by doing the same integral behind the horizon. This goes from, this is from 0 to minus epsilon, and this is from 0 to epsilon. Okay, that's because u is defined to be positive behind the horizon. Okay, what is happening here? What I'm doing here is, if you look at the behavior of the field, if you quantize the field, you open Birrell and Davis, you will find that the field has a property that if you write it in Kruskal coordinates, it oscillates very rapidly as you approach the horizon. Okay, and it also oscillates very rapidly on the other side of the horizon. What these integrals are doing is these integrals are picking up, these modes which are oscillating very rapidly at the horizon. Okay, so that's what these integrals are doing. But whatever it is, if you found these operators, I'll go and define these guys, and you can check that if you quantize the field, if you open Birrell and Davis, it would tell you that when you quantize the field, you find that there are some modes that oscillate as u to the I omega. And you can pick them up with high accuracy because they oscillate an infinite number of times near u equal to 0. That's why you can pick up the mode with high accuracy, even though you're doing the integral only for a short region here and only for a short region here.
This phi was a CFT operator.
This phi is a CFT operator, but I can still define it. It's an operator that is defined for all values of x. So in particular, it's defined for all values of u. So I can take phi and just do an integral over some parts of u. So using the same CFT operator, because the field.
It's not trying to satisfy some wave equation or something.
It has to satisfy wave equation for sure, because remember it has to give you the effective. It has to. That's what determines this. That's what determines. Right. So when you did this, the first thing you'd have to find about. So right now I just defined for you some operators, but I'm trying to give you intuition for why they make sense. If this equation is to hold, then it must be the case that this phi satisfies an approximate wave equation, because the right hand side comes from operators that satisfy an approximate wave equation in these parameters x. Okay. Okay, so now in terms of these operators, I can refine this property, and this is going to be the key thing. I'm just going to refine that equation. Okay. And so the question is, if you just take that, and in fact, here I wrote gx to gxn. In fact, the whole issue already arises once you're at 2-point functions. Okay, so I only need to take n equal to 2 to see this whole issue. And the properties you need are the following. You want that expectation of a omega. So first you want that a omega dagger is equal to 1. I'm not writing a delta function because I've normalized them using this, right? So I'm not writing delta omega minus omega bar. You want a tilde omega dagger is equal to 1. A omega tilde is equal to 0 is of course equal to a omega tilde dagger. Okay, so these tildes, they commute with each other. That actually comes from locality in the bulk. This is the fact that things on one side of the horizon commute with things on the other side. But more importantly, you'll also find the following. And this is equal to okay, and also that a omega twiddle okay, expectation value means expectation value in a typical state. Yeah. Okay, so I went to Birrell and Davies and I computed my Green's functions. Using that, I have the following expectation. I have the following expectation for the expectation values of these operators. Okay. I have so the transverse directions I could integrate over. I could integrate over using spherical harmonics. You're right. Actually, that maybe I should have been more careful about that. So let me define an L, which actually I don't care about here very much. Yeah. I also integrated a transfer. Thank you for that.
So you have many.
I have many modes. I have one mode for every L. They all have to satisfy this property. On the right hand side, you don't get any dependence on L because right near the horizon, everything is excited. Okay, so you'll get delta LL prime, but apart from that. So I'm sorry, thank you for that point. So it's true that these modes are not only labeled by omega, they're also labeled by L. And everywhere I should write a delta LL prime, but if you'll excuse me, I won't write it, yeah? But please remember there's a delta LL prime. If you open the papers, of course, all this is there. Okay, so now there's one last thing which is related to what Loga said. Remember these operators, and this is the only point where I'm going to introduce dressing. These operators had to be dressed to the right boundary. That tells you something about how these operators behave under the action of the Hamiltonian that moves points on the right boundary. So, what you can find is that if you compute the right hand side, you take the Hamiltonian, you act with the Hamiltonian, it moves operators on the right boundary. And that will give you two additional equations. It will tell you that H A omega is minus omega A omega. And of course the opposite, but H A omega tilde is plus omega A omega tilde. So while A omega reduces the energy with respect to the boundary Hamiltonian by annihilating an operator, A omega tilde increases the energy with respect to the boundary Hamiltonian. This is just a geometric statement that comes by looking at how the field operators are translated if you translate the boundary. So if you translate the boundary, and I have linked my point in the interior by taking a geodesic, then if I translate the boundary, the whole geodesic transforms. That gives you some transformation in this integral, and that gives rise to this answer. This is also, the famous but sloppy statement that the operators inside have the wrong energy, the particles inside have the wrong energy. But really it means this, okay? It means that if you dress operators to the right, then you find that for these modes, you get some commutators with the Hamiltonian there of this kind. Yeah. Okay, so these equations are important because the question is, can you find some operators in the CFT that satisfy all the properties on this board? If you found such operators in the CFT that satisfy all the properties on this board, then you're done. Okay? Then you have solved the issue, you've solved the problem. And the whole issue is, can you find some operators that satisfy this property? Okay, is this yes?
The states you were the states, the operators in
Yes, so I want the expectation value, these expectation values to hold in typical states.
the operators are searching in the
Space of all operators. No, you can find any. If you find an operator, I'll just declare that that's the operator in the CFT that matches the bulk field. You find the operator for me. Okay, so now I want to explain why it's hard to find these operators. Okay, but this is, if you've followed me so far, this is already some level of progress because this already defines the problem. And you're really working on projectors. The issue of projectors here would be, I don't know how to, I've actually thought of framing this in terms of projectors, but really the issue is what happens about fluctuations. Rather than talking about projectors, I could ask what happens if I look at fluctuations of these operators. So I think the fluctuations of these operators you would compute, and the point you would like to make is that the fluctuations of these operators behave approximately like free field fluctuations. So if you get another insertion of A omega, it clicks. But if you insert operators with different A omegas and A omega primes, then basically it just factorizes into 2-point functions. So maybe rather than answering the question in terms of projectors, I will say that you could ask this question for n-point functions rather than 2-point functions. But the only interesting objects that appear up to 1 over n are 2-point functions because I'm in a weakly coupled setting. I didn't quite answer your question, but yeah. This is true for all omega. Yeah, so once again, this omega I don't have to take to be like in the extreme UV or something. This omega can be around the scale of the Hawking temperature. It's some typical scale for the black hole.
So you will demand this relation.
Yes.
For omega up to what scale?
Omega being up to 1 to something much smaller than n. You see, the result I wanted here was also that it should hold up to 1 by n. So if you make it hold for omega around Hawking scale, I'm happy. If something happens in the UV, then I'll say that's a prediction of the CFT or something. Right? So I won't trust anything. So this is all very reasonable. Okay, so I want to explain why this is impossible. At least I hope I can get to that. Wow, going much slower than I thought. So the first question is, what about the A omegas? Okay, what about the operators? Remember, these A omegas are operators outside the horizon, and A tilde omegas are operators inside the horizon. Okay, the way I defined it, because A omegas were done by doing an integral outside for U negative, and A tilde omega for doing an integral for U positive. So A omega actually is very simple. You take the CFT operators, you take the CFT prime. So here the idea I had was that there is some bulk field. This bulk field has some mass. Corresponding to that, there's some CFT operator. The CFT operator is some primary operator. I take it and I divide it by some factor that you can find. For instance, we found this factor explicitly for ADS3. But in other cases also you can define this factor. If you do this, you will find that you will find these operators A omega. So there's no problem in finding these operators. Okay. And this O omega really just means O of t on the boundary e to the minus I omega t. Actually, sorry, maybe I want e to the plus I omega t. So I just take this O omega, I integrate it, or I take the boundary operator, I integrate it in time. I define its mode, and then I have to normalize the mode with some factor that one can determine explicitly. That gives you these operators A omega that satisfy these properties. And that satisfy this property. Okay. So this you can show. So there's no problem in finding the operators A omega. If you wanted to find this, you would get it by just doing quantum field theory in curved spacetime. You would get this factor C omega. So the question is, it's clear just from symmetries that this operator A should be related to the boundary operator in this way. The question is, how do you normalize it? To find the normalization, you have to do some calculation, which is the QFT in curved spacetime. It's classical meaning it's a semi-classical calculation. Yes, that's right. You could do it in any ADS, but you can't do it explicitly for higher ADS. You can define it, of course. Yeah. Okay. So this is for an ADS-free black hole. Okay, so this is the answer for these A omegas. There's no problem in finding these operators A omegas. We are half done. The question is now, can you find the operators A tilde omega? Okay. Okay, so this is not exactly, by the way AMS phrased it, but I'm at least at a point where I can explain. So the AMS claim was that A tilde omega do not exist or cannot exist. So why can't they exist? I'm now going to give you two arguments. There are other arguments you can construct why they can't exist. Okay.
Does that mean that the CF doesn't know?
If these don't exist, then yes, the CFT doesn't know, or maybe there are many possibilities. Maybe you see this right hand side I got by doing a calculation in the Kruskal spacetime. Maybe the Kruskal spacetime is wrong. Maybe there's a firewall. Maybe spacetime ends. Right? So, or the CFT doesn't know about it, or whatever. Then you know. So maybe something interesting happens if these operators don't exist. It's not clear what happens. Maybe typical states are not Kruskal states. Whatever. Okay, so I'm going to give you these arguments. Why is it that A tilde omega can't exist? So here's argument one. You see, we said that we want this expectation value. I'll put back the states. To be 1 by 1 minus e to the minus beta omega. Very good. But we had all that discussion about how typical states are like almost thermal states and so on. So this is also the same as 1 by z of trace of e to the minus beta h, a omega tilde, up to 1 over n. I forget about the 1 over n. Okay, so is this fine? If I found such an operator, it holds in all typical states. Therefore, it must be the case that it must be also true in the thermal ensemble. Yeah, this z is the partition function. Very good. But now the trace is cyclic, right? So let me take this a omega tilde dagger. Here I use the fact that in a trace of AB is the same as trace of BA. Okay. But now I know the commutator of a omega tilde dagger with e to the minus beta h. Okay. In fact, a omega tilde dagger has the property that it reduces the energy. So this is actually the same as e to the minus beta omega trace with e to the minus beta h, a omega tilde dagger, a omega tilde. Yeah. But now I also know the commutator of a omega tilde with a omega tilde dagger. So let me just write it here. A omega tilde minus 1. Yeah. So what have I found? I found that the trace of this operator, a omega tilde dagger, was the same as the trace of this operator, and there's a minus 1 here. If you solve this equation, you will find that, if you just solve this equation, you will find that the trace of a e to the minus beta h, a omega tilde dagger is smaller than 0. Why is it smaller than 0? Because you have a minus 1 here. Right? Sorry, I hope I got this right. And please check my algebra if I didn't get it right. A omega tilde is equal to this. Yeah. So yeah. So yeah, it's, you see, if I have this expectation value on the right hand side, I have a minus 1. It's e to the minus beta omega. So if I take the e to the minus beta omega to this side, what I found is into 1 minus e to the minus beta omega here. A omega tilde dagger, a omega tilde is a omega tilde dagger minus 1. Yeah, it's fine, no? I think it's fine. So this into 1 minus e to the minus beta is trace of e to the minus is, yeah, e to the minus beta h is trace of e to the minus beta h with a minus sign. A minus sign is here. A omega tilde is, yeah, I took this trace. So this is just minus e to the minus beta omega, I think. Minus beta omega. Yeah. Okay. So that tells me that I got, the answer I got is actually that trace of e to the minus beta h, a omega tilde dagger. I might be messing up the algebra, but it's always negative. Yeah. Minus e to the minus beta omega by 1 minus e to the minus beta omega. Okay. But this is a contradiction. Not only is it the wrong answer, it's crazy because it tells you that this is a negative, this is giving you a negative answer, but this is explicitly a positive operator. So this is a positive operator. And how could it be that it gives you a negative answer? Yeah.
When you wrote your A,
Huh.
You had started from the horizon, right?
I started the horizon, I integrated out and in. Yeah. At which boundary? I don't have to go to the boundary. I just integrate close to the horizon to pick up these modes. It vanishes once you're far away from the horizon. You don't need to be very specific about that.
If it doesn't vanish very fast, then it's not an operator.
Why?
It has to go very fast so that
the smearing function you only needed to get to make sure these were not delta function normalized. Like that's just some modulation of omega.
Then it's not operator norm. If the operator norm,
I don't think there's a problem with this issue of whether it's an operator. Yeah. By the way, so let me just explain what the problem is. The problem is that you're saying, the contradiction here is with the fact that these operators have the wrong energy, but A omega tilde, we are saying increases the energy, but we are still saying it's an annihilation operator. It has the property that its commutator with its adjoint is 1. Oh, did I not write that? You see, the commutator with the adjoint is 1. But it doesn't make sense to say in a finite dimensional Hilbert space, you have an annihilation operator whose commutator with its adjoint is 1, but the operator has the property that it actually, increases the energy rather than reducing the energy. Okay? The way you find that annihilation creation operators have the right commutation relations, it has to be, it also has to do with the fact that annihilation operators reduce the energy. And this just has to do with how the states grow with energy. Okay? So annihilation operators have to kill some states. They can't map you from a lower dimensional space to a higher dimensional space. If you did that, then you would be in trouble. And this is a manifestation of that.
you didn't need typicality. So in the end, your contradiction was that this trace came out negative.
In the end,
the first line in 1, you didn't really.
I needed to go from here to here. I needed to say that this expectation value was the same as this trace.
Let's say you didn't know that equality.
I didn't know that if I just said, can you find such an operator in some state, you would find it in some state. If I said, can I find an operator in some state that has this property, there's no problem. The problem is that you want this expectation value in this state to be also the same as the trace.
The point of what I'm saying is that equal to that positive number you wrote.
Equal to this.
This number was never used later on.
This positive number.
Yeah.
Yeah, this positive number was never used. I just computed the state. I wanted it to be true and I got a very different answer.
Trace to be some number.
Yes.
Capital C.
Yes.
And by positive definiteness, you know that C has to be positive.
Yes.
But you found it to be negative.
Yes.
You didn't need the first equality.
Yes, but then someone could have said, what was the point of the trace? Maybe that your trace has the wrong answer, but in the state that I'm interested in, the black hole state, I still get the right answer. You see, why is the trace relevant? The question is, can you find, maybe the pedantic discussion. The reason the whole discussion of typicality was relevant was to say that the trace is relevant. If I just said that I have one state, which is the black hole state, and it's a very atypical state. No, also to go from here to here. I want to say such an operator doesn't exist, right? I wanted this to satisfy some property.
So what I'm saying is, you're already assuming on that board that such operators exist, right?
I'm assuming on that board such operators exist, and
What is the point?
that they had to satisfy these within a trace. They have to satisfy this commutation relation within a trace. If I just say that for one state, I want an operator to satisfy those properties, there is no contradiction I'll be able to derive. I want them to commute within the trace.
Have some sort of typical state. You derive some operator relations.
Yes.
On those operators, right?
Yes.
And there's already a contradiction in that operator algebra.
In this operator algebra,
there is already a contradiction.
if I demand that this expectation value holds in all states, and if I demand that this also holds in all states, then there's a contradiction. If I'm willing to say that this is not true as an operator equation, but it's, yeah, you're right. Within this operator algebra, there's a contradiction. But if I'm willing to say that this is not, maybe this is, I should have written it a little more carefully. If I'm willing to say that, these relations don't hold as operator relations, but they hold as expectation values for a small set of states, then there would be no contradiction. If I demand, you're right, there's a contradiction in this operator algebra in saying this and this. Yeah. But you see, the operator algebra is never relevant because we never measure these commutators as operators. What we really measure is that the expectation value with some other operator A is the expectation value with A. I didn't write this, but I should have written that really this holds, you want this to hold within expectation value. And then, I said that, because it holds in typical states, I'll assume that it holds as an operator relation. What you really, if I didn't want that to hold in typical states, if I just wanted it to hold within some small class of states, then I could get some operators that, and in fact, I'll show you tomorrow, that behave like this, but in a small set of states. Yeah.
Somewhere you are using the fact that the beta is positive, right?
Somewhere I'm using the fact that the beta is positive, yes.
Because, I mean, what you are saying is that the aim
Yes.
should.
Yes. Yes. As beta is del S by del E. I mean, beta is telling you how the entropy is changing with E. So beta is del S by del E, and it's telling you that beta is, so exactly, beta is positive, tells you there are more states at higher energy than there are at lower energy, which was important here. I mean, otherwise you would have got a positive answer here if beta was negative. So, and that's exactly the contradiction, yeah. Okay. Yes.
I still didn't get
Yes.
the answer to my.
Yes.
This point number 1 that you're starting, you just derived a contradiction. I mean, the trace is just there as a mathematical object, right? Whether I can measure it or not is a separate thing.
Yes, but do I want the, but I use the
You already derived the contradiction that this trace has a negative value.
Yes.
And that's already a problem.
It's a problem, but to derive the contradiction, I had to assume that these relations hold as operator statements, the commutator between h and a tilde omega, and this commutator holds as an operator statement. If I'm willing to say that it doesn't hold as an operator statement, but holds as an expectation value for a small class of states, then I would not be able to derive the contradiction.
First line is still not relevant.
The first line, you're right, is not relevant for this particular case. Yes, you're right. That for the first, yes, okay, you're right that this, yes, you're right that for this specific contradiction, what I needed to demand was that these relations hold within typical states, and therefore I can interpret them to be operator relations. Yes, you could have derived this without writing the first line. Yes. I just wanted to emphasize that the answer you expected for the first line was this, and you got something else, but you're right, you could have derived the answer without writing the first line. Yes. These are computed in typical states. This is the whole discussion we had. I'm sorry I haven't written it, but this is the same psi that we had earlier. It's the same psi. We want these relations to hold in all typical states. Yeah. Oh, 5. Huh. Huh. Yeah, we already have 5. Yeah. Huh. Huh.
But what if I consider extended operators, which would then, I mean, of course, the whole measurement theory would be, but extended operators, then you can't just project out quantum.
Let's postpone the quantum mechanics discussion. Yeah. I don't. First of all, this issue here is not about distinguishing states. I just wanted to say that, yeah. Okay, but let me just say one thing, and then we can come back to this distinguishing thing. Maybe. Well, I want to know if there are measurements. Actually, here I want to know if there are some operators you can find in the CFT that give you some expectation values. We'll come to the issue of whether you can distinguish states. You can allow extended operators here. You can allow whatever operators. Extended operators also fall within the set of quantum mechanics. They're just operators. They're not local operators. But there's some operator, any operator in quantum mechanics. Can we just, let's come back to this a little bit, yeah. Okay, let me give you one more, since you're already at 5, I want to give you one more argument and then we will stop, yeah. The other argument is, so this is one argument. The other argument is, well, I said that, you see, let's look at the following number operator. This is the number operator you would find in Birrell and Davies, which is, I'm sorry, just give me 2 minutes more and I'll stop. Plus A omega dagger. You know, this is the operator this is the so-called Unruh number operator. A omega tilde minus e to the minus beta omega by 2 A omega dagger. Okay. And I have to normalize it, but I'm not going to bother normalizing it right now. This is the Unruh number operator. And, you know, if I believe all those relations hold, then I expect that in a typical state, the expectation value I want to get for n is 0. Okay. I want the answer that the typical expectation value for this n should be 0. And you can check if those relations hold, then you will find that the expectation value would compute for n is 0. This is saying that if you have an infalling observer, that observer measures no particles. That's what we expect. However, here's a paradox. Paradox is, well, Let me compute the trace of n. Because n is 0 in almost all states, right? You see, I said n is 0 in typical states, and therefore, I expect that the trace of n is also equal to 0 by our discussion of typicality. You agree with this? Because I expect the expectation value in any such state is 0, and because any such state is close to the trace in the microcanonical ensemble, I expect the trace in the microcanonical ensemble of n is equal to 0. Okay, but now I'll give you another way to compute the trace. One nice thing about traces is we can compute them in any basis. They don't care about which basis we're using. Let me use the number eigenstate basis. Where n is the operator, it's the number operator.
Any basis is okay if you have included all states.
Yes.
But whether
Yes.
states you are
So in the paper that I referred to, we actually spent a lot of time worrying about these edge effects. And so you're right. There's a manifold of states, and in principle, you can always change basis within that manifold. But you're right. There are some edge effects which we actually spend some time persuading ourselves will not matter. It's actually not in the original AMPSS papers, but in the paper we had with Kyriakos, we spent a lot of time worrying about these edge effects. Yeah. So you see, I can change base. This trace is done in the microcanonical ensemble, which is looking at a trace of energy eigenstates. But the number operator, you can see, approximately commutes with the Hamiltonian because of those commutation relations. Therefore, instead of computing in the microcanonical basis, you could have also computed the trace in this number basis. Now, the number basis has the property that A omega tilde is equal to 0. It's very easy to persuade yourself this is the case because A omega changes the eigenvalue of the number operator to being n minus 1, whereas A omega tilde doesn't change the eigenvalue because it commutes with the number operator. Yeah? So A omega tilde keeps the eigenvalue n, so you get n into n minus 1, and you find this is 0. And that's also the case for n A omega tilde dagger A omega dagger. So in the number eigenbasis, there are no cross terms between A omega tilde and A omega. Okay? And you can do a short computation, which I won't do, but which will tell you that in any number eigenstate, using the positivity of these operators, you will find that the expectation value of n is greater than equal to twice e to the minus beta omega by 1 minus e to the minus beta omega. Okay, I won't go through the algebra, but it's simple to persuade yourself that this must be the case in any number eigenstate. But now I can do the trace in the number eigenbasis. This is a positive operator. Therefore, I will find the trace of n is, if I normalize it correctly, is positive. And in fact, not only is it positive, if I normalize by 1 by e to the s, then I have concluded from here. But now I'm in trouble because this is not the same as 0. So this is another reason, another argument that tells you you can never find operators that have this property. Okay, so this was the argument. Actually, this was not given by AMPSS. This was given by Marolf and Polchinski in one of their later papers. Yeah. Okay, so here's an argument that says that you wanted some operators which had the right expectation value. But if they had the right expectation value in typical states, the trace should have been 0. But look, I can compute the trace in a different basis, and then I'll find that the trace is positive. N is the eigenstate. Sorry, N is eigenstate of this operator. This is this number operator. This is NA is a different. It's the infalling number operator. NA is the number operators measured by the infalling observer. N is the number operators measured by operator at infinity. Observer at infinity. So the key point here is because the Hamiltonian commutes in the microcanonical ensemble, I can change basis and I can compute the trace in this basis. And by doing that, I find that the trace is not what I wanted. This is not the bond rule paper. This is the paper before the bond rule paper. The bond rule paper we haven't come to today. We'll come to tomorrow. Yeah. So this is I forget the reference exactly, but there was an AMPSS paper and then there was a Marolf Polchinski paper which was in 2014 or something. You will find the reference. This is only Marolf and Polchinski.
This Emmy is the Minkowski number.
Yes, it's a Minkowski number. That's right. That's right. Okay, so this is actually a good time to stop. I hope at least, let me just summarize what I said. What I said was, if you want, the CFT to describe the black hole interior, then you want to find some operators in the CFT that satisfy this property. In a typical state, you find that, there are various arguments you can give. Notice the special property of these arguments is all these arguments rely on a trace. They rely on saying that these properties of these operators hold in all states or in all typical states. And therefore, if you do some trace, we can do some trace by using that, and then we can play various tricks like the cyclicity of the trace or changing basis in the state, and we can derive some contradiction with what we had. So it's very important that all these arguments involve a trace. And why do they involve a trace? Because of the discussion we had earlier, which is that we expect them to hold in almost all states, and therefore you can take a trace and you expect that the result will still be true. So if someone were to say, well, I can't find these operators that satisfy these properties in all states, but black holes are very special states, and I don't want these relations to hold within traces, then there would be no problem. So if someone said, the space of black holes is a very small set of states and most other states are something else, then that would be fine. Okay, so tomorrow I'll try and explain where state dependence comes in and what the violation of the Born rule is. But at least I hope this gives you a sense of where the first part of the question, which is that you can't find these operators until you do something unusual, which we'll discuss tomorrow.
For small black holes, these problems will not.
For small black holes, you cannot immediately formulate these problems because small black holes are atypical states. It might be that you can formulate an ensemble for small black holes, and then you could, rather than talking of, you see, small black holes never dominate the microcanonical ensemble. So these paradoxes, as they stand, don't work for small black holes. For this reason, by the way, they also don't work for flat space black holes. Like for flat space,
Black holes aren't a flat space.
yes, that's right. So for flat space black holes, there is no such firewall argument. But the fact that it's not known doesn't mean that it doesn't exist. Maybe you can define a more sophisticated ensemble and do something of this kind, but it has never been made, as far as I know.
But Mathur's original argument was also for that.
Yeah, but Mathur's original argument was a different argument. It didn't rely on this. And I think that argument you completely resolve once you realize that degrees of freedom in one place need to be identified with degrees of freedom in another place. These arguments are not relying on that. So you can say, fine, I don't have locality or identified degrees of freedom, but that's not helping you get rid of this issue. So this is a separate issue from Mathur's issue or the first AMPS issue. Okay.
Yeah, are there any more questions?
Sorry for going over time, yeah.
Any questions online? I think if there are no questions, then let's thank you.